Thanks for everyone for being here. Today I'm going to be talking about how Red Hat is experimenting with different deep learning architectures to address various business problems. Originally I was only going to be talking about recurrent neural networks, but I decided to add in a couple of other deep learning models that we've been playing with because I thought it might be of interest to this crowd. And so a quick rundown of what we're going to do. I'm going to start off with a brief background of deep learning just to get everyone on the same page. From there I'm going to go into a model that tries to predict customers who are going to drop their subscription. So Red has a subscription model, and so that's something that we're obviously interested in doing. The second model is going to be a model for predicting whether or not a customer will escalate a support case. And both of those first two models I mentioned are recurrent neural networks. The next model is a word-to-vec model that one of my colleagues who's at PyData this week, Diego Fernandez, worked on. And then the last model is my implementation of a paper from Microsoft Research, which is basically a deep learning take on semantic search. And so I tried to make my slides really, I try to design them so that they encourage exploration. And so you can find my slides right now on my website. So if you Google my name in quotes, that should be the first link, and then you can find the slides there. And I have links basically scattered throughout the slides. I encourage you to click on them, including most of the images are linked to their sources, so you can have more information. And so what is deep learning? It's a model that is loosely inspired by the brain that learns complex associations between variables. It is not magic, despite what media might have you believe these days. It is just math. And so what is actually happening, this is basically your typical feed-forward neural network. And if you guys were at the graph talk yesterday, you know that these circles are nodes and that the arrows are edges. And basically what you're trying to do is each of these groups of edges represents a matrix in your model. And so all deep learning is basically a series of linear algebra operations that then get passed through some sort of nonlinear function typically, and then they try to make a prediction. And so what you're trying to do with deep learning is learn the parameters of these matrices that minimize your error, right? And so the way that works in practice is that you randomly guess your initial weights for these parameters. You calculate the amount of error you have, and then using calculus and partial derivatives, you perturb these weights a little bit constantly until you get to an error that's acceptable. And so I think a lot of data science today you can do without really understanding deeply the math behind the models. Deep learning is not at that state yet. So sort of step 0, if you want to get into deep learning, is to get Strang's linear algebra and its applications. Go through that, get a really good understanding of linear algebra, and then you'll basically be ready to get into the software part. And so on the previous slide, I mentioned how later layers tend to learn more and more abstract concepts in the model. And that's sort of hard to conceptualize, I think. And so I like to put in this slide to give you basically a visual indication of what that means. And so these results are from a paper a few years ago that really put convolutional neural networks on the map. And convolutional neural networks are basically this specialized form of a neural network that's really good for computer vision. In this particular task, what the goal is to, it's object recognition in images, right? And so a few years ago, this competition was held. This particular research group used a convolutional neural network. They achieved unprecedented results, which was awesome, right? But the really cool thing is that when they looked at what the lower layers were learning in this model, they were learning these really interesting filters, right? So learning things like edges oriented in different directions, color gradients, and other types of patterns. And so you can imagine how if the early layer is learning these simple features, how later layers might combine, things like edges, circles or something like that. And then a later layer might say, okay, these types of circles are wheels, these ones are eyes, and at the final stage, you can then make a prediction, car, face, etc. Okay, so feed-forward neural networks are really awesome. They're really powerful, but they have one significant limitation, which is that they require a fixed size input. And so recurrent neural networks are basically a solution to that problem. And the way recurrent neural networks work is they basically, and so why would we want, variable length data? So time series, right? And so if you're in a subscription model like Red Hat, some of our customers have been with us for months, some of them have been with us for years. So how can we incorporate all of that data into a single model? And so recurrent neural networks are the answer in a lot of cases. And so the way they work is they basically stack up or put feed-forward neural networks side by side, and then they connect the hidden layers from the different time steps, right? And so if you remember from the first slide, what we're trying to learn is those three matrices, right, of those layers of connections. We basically just add another matrix here. And so with the recurrent neural network, you're trying to learn, in this particular case, the matrix that gets dotted with your input, the one that gets dotted with your hidden layer to the output, and then a third matrix that gets dotted between the hidden layers, okay? And so each of those matrices are used for each time step, which is what allows these models to be trained. Okay, and just a quick aside on recurrent neural networks, how cool they are. Google put out this paper a couple years ago where they used a recurrent neural network to translate English to other languages. And so basically what that looks like is they feed in words from an English sentence, and then they output, the predictions are the words from the language that they're trying to translate it to. And so they achieved really great results. But the really cool thing, again, was that when they fed in an English sentence and then took the last hidden layer and took the first two PCs of a principal component analysis and plotted those sentences, what they found is that semantically similar sentences mapped to close to each other in the space, which is really like fantastic, right? So the point there is that these models can be really powerful. Okay, so that's a very brief introduction to the theory. The tools that are available are summarized basically on this slide. And so the major backends basically that people use these days are Theano and TensorFlow, and they basically do the same type of thing. They are mathematical expression libraries where you basically define how your data will flow through your model, and then you can train it from there. And so I mentioned linear algebra is a good thing to learn. Also, like sort of step 2 is functional programming. And so if you're not used to functional programming, so this comes up in like functional programming is like things like Scala as well, or Spark has a lot of functional aspects to it. Basically, it's different in that you're not, when you like define like a particular operation, so when you take a dot product of your variables, it's not being calculated right there. It's not being executed. You're just like defining the graph of how the computation is being performed. And so that's basically what this image is trying to represent. So Theano and TensorFlow, though, are basically very similar things, doing very similar computational graph type things. And so also I want to emphasize that both of these libraries are broader than deep learning. For example, Theano, I met a woman here from Duke, Shin, who their lab is using Theano to do variational inference. And then if you're familiar with PyMC, it's this Python library for doing Bayesian inference. They also use Theano as your backend. So it's this really powerful library for designing models, basically. And so the last thing I want to mention is these two wrappers, Lasagna and Keras. They are pure deep learning stuff. So they basically build on Lasagna and Keras use Theano. Keras can use either Theano or TensorFlow as the backend. But they like basically implement common deep learning models to make it a little bit easier to use. Okay, so getting to the model. Actually, I didn't start my timer, my bad. So yeah, I'll definitely need that cue. Yeah, so the first model. The motivation here is that Red Hat offers a lot of products, right? Most of the customers are able to take advantage of those products. Some of the customers have trouble getting the most out of their subscriptions though, right? And so we basically want to help those folks out. And so the hypothesis that we're going to be working with when we're building our model is that a customer's decision to keep, drop, or add their Red Hat assets is at least partially influenced by their experience with Red Hat. And so external factors though, like market trends, also probably play a role. We're not going to be incorporating those in this particular model, but in the future that's obviously something, that's more information that we would like to include. And so this is just a quick graphical representation. Red Hat has these products. A lot of these companies are like using them in really cool ways, but some of the customers might be a little overwhelmed with the offerings. So how can we find those people and reach out to them? Okay, and so the basic model building pipe or data and model pipeline is outlined right here. It's very typical for data scientists. You collect the data from your different sources, perform some intermediate machine learning and data science steps on those data sources. And then in this case, because we're working with a recurrent neural network, we'll put that data in a time series format. And in this particular case, we are looking at 18 months of historical data, and we're trying to forecast 6 months in the future how many of their assets that they're going to be dropping. And so just a few general recommendations when you're doing data science, at least have come in handy for me, is to be granular. And so if you have a particular component of data that has subcomponents, use those subcomponents. That's just more information for your models to learn from. Also, use bins instead of aggregations. And so, for example, Red Hat has cases, right? Support cases. Customers make comments. And so your first instinct might be to say, okay, let's see how many comments this customer made this month. So if a customer made 100 comments, though, in a month, they could have made 100 comments on a single case, or they could have made 10 comments on 10 different cases, right? And that gives you very different information, I think. So try to be granular, or try to use bins. So the number of times a customer made 5 comments, the number of times a customer made 10 comments, et cetera, et cetera. And then finally, take advantage of unstructured data. This probably doesn't need to be really advocated here, but if Red Hat sits on a bunch of text, that's a ton of information about our customers, right? And so try to incorporate that into your models if possible. And so I am a software engineer, a senior software engineer actually, a recent promotion, on the customer experience and engagement team. And that means we have basically access to these 3 different data sources. The customer portal, which is where we basically log all of the web activity that our customers are, all of their activity on the website. We also have the cases data that I mentioned before. So if a customer has an issue with their software, they open a case, it creates this dialogue between Red Hat and the customer. There's a lot of information there. And then finally, we have the assets and entitlements data, which are their actual subscriptions. And so we know like what type of product it is, how long they've had the product, what quantity they have of that, whether or not they've had evaluations or betas before they got before they bought the product, the full product, et cetera. Okay, and so I'm just going to sort of walk through the basic data pipeline right now. The first step is to collect the portal data, and this slide's actually out of date. So we store this data, we used to store it, well, we still do actually, store it on a Hadoop cluster. And so the way I would process it before was using a pig script to do some MapReduce stuff, but we actually migrate a lot of this into a Redshift database now, and so a lot of this is actually out of date. But regardless, the point here is you're trying to count the number of times that these customers are looking at different page types. The second one is probably more interesting, in my opinion. And basically, what we're trying to do here is we're trying to capture sort of the behavior of the customer on the website for the month. And so you can imagine how the web pages that a customer looks at during a certain time period are probably correlated together, right? They're probably like giving you information about the particular problem or the type of technology that the customer is interested in at that time. And so with that in mind, what we tried to do here is basically represent, we built this big matrix where each row is a specific account at a specific month and time, and each column is a different URL that they could have visited on the customer portal website. And we basically, the values in those columns are the proportion of time or the proportion of page views that the customer visited that particular URL for that month. And so what we then did, because we want to sort of learn this like latent explanation of that type of behavior, is did a singular value decomposition on that matrix. And so if you're familiar with like matrix decompositions, that's basically exactly what we did here. This matrix is very big and very sparse. And so if you guys haven't dealt with that, a good solution is to use a compressed matrix form. In this particular case, we use a compressed sparse row matrix. And so it basically changes the way the data is stored on the back end to make it a lot smaller. You basically ignore the zeros of the way it's stored. And so the second or the third step, I guess, is to collect the cases and assets data from the databases. And this is just a bunch of MySQL queries. And then we map all of that data to the account ID, year, and month, which makes accessing it easier when we're trying to write all of this disparate data sources out to a single time series format. For step 4, this is another idea. I mentioned Diego Fernandez earlier. This was his idea originally. And so the idea is that we have over 1 million support cases, but only a very small fraction of them do we have customer feedback on how they felt about the case. And so Diego's idea was like, maybe we could build a model that predicts the customer response and use that to make predictions on all of the cases that we don't have that response for, and use that data then in our model. It's like sort of, it's not quite semi-supervised because we're not going back and correcting it, but that's approximately what it is. And so basically we did exactly that. We used a gradient boosted machine using XGBoost. And so if you're familiar with Kaggle, that's sort of like the bee's knees over there. And what we found is that we can basically, we can't predict the exact score, but we can basically distinguish between positive and negative experiences. And so that's what we did. We went back for every case that we don't have a support score or support score for, we assign it that, and then we incorporate that data into the model. And so again, being granular and talking about bins, we count the number of times that they had like a 1 or a negative versus a positive, instead of just like averaging the predicted score that the model gave us. And yeah, like I don't think I emphasized this point at the beginning. Neural networks are definitely not magic, right? Because everyone on Kaggle, or for a lot of competitions on Kaggle, people are using XGBoost and they're winning, right? There are other competitions where neural networks are working better, but it's really, there's definitely interesting dynamics there about the different properties, basically, of how these models are trained. For the next step, this is also pretty interesting. So we wanted to, customers are opening these support cases, right? And we want to basically capture what they're talking about in their support cases. And so this work was done by Michael Coleman, who was an intern with Red Hat. And what he did was performed a latent Dirichlet built a latent Dirichlet allocation model on the case documents. And what a latent Dirichlet allocation model does, it basically models your document as a bag of words, and it says the distribution of these words is basically based on the mixture of topics that define that particular document. And so once you build this model, you can then assign a vector of topic distributions to new documents. And so that's basically what we did. We built this model, and then we went back over all of the cases and got their topic vector, and then we basically sum those up for a month, and that gives you approximately a count of how many times they were talking about cases of that particular topic. Okay, and this is basically just a quick example data. This is how I structured it in a text file. You probably don't want to store this in a text file usually because it can get really large. But this is just to give you a sense of what it looks like. So a bunch of features. And this is like, I think, like this is 1 month of data. And so the way I have it set up is like there's lines of data for each account, and each line represents a different month, right? And so this data can be very big, which is probably unsurprising because it's time series, right? So not only do you have your account dimension and your features dimension, but you have a third dimension, which is time. And so you can get like huge amounts of data. We decided to store it as a memmap, a NumPy memmap array, which stores your data on disk, but allows you to access it just like it was a normal in-memory NumPy array. This might not necessarily be the best solution for you. It can be really slow to access the data once it's in this format. And so I basically do some parallel processing when I'm training the model, where as one particular batch is getting passed through the model, I'm fetching the next batch from the memmap array, so I don't have to wait for that on the next iteration. And so yeah, the shape of this, like I mentioned before, is it's a 3-dimensional matrix. And so like if you're not used to linear algebra again, that can be kind of confusing. And so another way to think about it is that it's a list, a Python list, where each element of the list is a matrix. And so the first element, for example, belongs to our first account, and its rows are the time steps, and then its columns are the features. Okay, cool. So now we're ready. Now we've got our data ready. We can train and test our model. And the only sort of trick I want to draw your attention to is that with recurrent neural networks, right, we're trying to predict an output at every single time step. With our model, we don't necessarily, it doesn't necessarily make sense to make a prediction at every time step because the customer might not be at risk of dropping assets, right? If they don't have any assets expiring, then it doesn't make sense to predict that some assets are expiring, right? And so the way to handle that is to basically mask your error function. So any month where they don't have assets expiring, you multiply it by 0, essentially, and that takes out that part of the error, and so that error doesn't get back propagated through the model when it's training. You then build the model, and so if you guys were at the Keras talk yesterday, using something like Keras or Lasagna is probably the way to go. It makes it a lot easier. You guys can look at this later. I used Lasagna originally because Keras wasn't available when I first started developing this model, but I've used Keras since, and I actually like it better, and so that would be my personal recommendation to you if you're just getting started. From there, we're ready to train the model. Nothing really crazy. Just beware of overfitting, good data science practice. And so I guess I also want to emphasize again that knowing linear algebra and understanding functional programming will make working with these models a lot easier. So even for people who know this stuff, like debugging in Theano can be pretty gnarly. And so like if you don't know that stuff, you're gonna have a very, very hard time. So take the time to just like sort of learn these concepts first before you like really start digging into the deep learning stuff. It will make your life a lot easier. Next step is just testing the model. The results you see here are just to emphasize that the recurrent neural network performed better than either a gradient boosted machine or a linear model. Sometimes, depending on the metric, 10 to 20% better. These are predictions. You can see there's still a lot of noise. There's a lot of way to go. But basically, what I want to draw your attention to is this table here. And basically, what this table tells us is that if we were to try to identify the customers who were the most at risk of dropping their assets, using a naive approach where we just look at the potential number of assets that could be expired versus the recurrent neural network, the recurrent neural network detected 100 more than the naive approach. And so how am I on time? 5 minutes? Okay, I'm gonna hustle through this. We also built a model for predicting predicting customer escalations on support cases. So a customer opens a case with Red Hat when they have an issue with their software, it creates this dialogue, et cetera, et cetera. We basically did a very similar approach to the asset model where we get a bunch of features, put those in time series, and try to predict. This model is still very experimental. You can see this is the distribution of predictions for truly escalated versus not escalated. You can see that the escalated are being shifted slightly to the right, but there's still a lot of overlap. And the potential impact of this is, so like if we looked at this number of cases for a given time period, and what percentage of the truly escalated cases does the model capture? And so with the recurrent neural network, we detected 20%. Using the naive approach, we only got 15%, so that's a 33% increase in our true positive rate, which is good, but there's still obviously a long way to go in terms of that model. And so I want to just quickly point out this model that I'm working on right now. The original customer escalation model was using like some latent semantic indexing of the text for the cases to as the text features. I'm now working on a model that sort of is jointly learning the text with the other case features at each time step. And the way it's doing that is it's doing like some convolutional neural network stuff within each time step within the recurrent neural network. And so I have my code on GitHub if you want to check that out. So that we also did a word-to-vec model. I'm not going to spend a lot of time. I will point out my batter pitcher-to-vec model. I learned some distributed representations of Major League Baseball players by trying to predict the output of a given pitch. So check that out if you're baseball fans. But what we learned on this model, these are actual examples of analogies that we learned from our distributed representations. And so you can see that bash minus shell shock plus Heartbleed equals OpenSSL. And if you're up to date on your Linux vulnerabilities, you'll know that Shellshock was a bash vulnerability and Heartbleed was an OpenSSL vulnerability. So that's pretty rad, right? Yeah, and these are just other examples from our actual data set that we were able to learn. Finally, I've been experimenting with a deep semantic similarity model that was first described by Microsoft Research. My implementation is also on my GitHub, and the way this works is, so if you're familiar with typical search, what they usually do is do a TF-IDF matrix, and they basically take the cosine similarity of those vectors, and if they're really similar, then those are the results are returned. This approach tries to model those latent, like semantic vectors using a convolutional neural network again. And so they learn these latent vectors by performing these convolutional operations over the text, and then they take the cosine similarity of that and basically pass it through a softmax function. That's what allows you to train the model. And that is it. I don't know if we have any time for questions, but I appreciate it. Thank you.
We have time for one or two questions.
Okay, sweet.
This is for posterity.
So you had a layer in your model where you're running an SVD on your web page views, which are huge sparse matrix, but the SVD is going to be dense in general.
Yeah.
Right. And yet later you're doing LDA because you have count value data. So why not use count value data for the web pages?
Yeah.
And treat all the web page views as a document, and then you're capturing something that's more like the sparsity. Have you guys tried something like that?
That's iteration 2. That's what we're working on. Yeah, that's a very good observation. He makes a really good point. So basically, rather than treat the document as like as we did with like the proportion of views being your vector, you can treat it as counts, just like the latent Dirichlet allocation model, and that like allows you to do the latent Dirichlet allocation modeling basically, which hopefully will lead to better results. We would expect that it would.
Another question? All right, well then let's thank our speaker one more time.